that in a minute. So, the line down the middle is meant to signify that the molecule on the left is passing through what's becoming a shock wave, a bit of a traffic jam, and out the other side and goes downstream into region 2. If you note at the bottom, it says typical shock wave thickness is 1,000th of a millimetre. You can imagine what you're really trying to get that poor CFD code to do, can't you, and the size of the actual cells that we use. Okay, so what happens when a molecule goes across a shock? As you can see here, so 1 is before, 2 is after. Because of the effort going through and the losses, the Mach number goes down and the speed goes down. The pressure goes up, as does the density and the temperature. The entropy, S, goes up, which means we're losing the amount of energy to do useful work. The actual total pressure has now dropped. We've lost. So that's our measure of efficiency, if you like. And the total temperature is the same. So that's actually quite a good test of, for example, a CFD code or for an experiment to make sure that that's actually true in the measurements that we're taking. Okay, so these are the same things all written down, except for a couple of others. Now, the top one, m2 squared, that's the Mach number on the other side of the shock. Notice that, as messy as it looks, it's actually not too bad because it's just got gamma equal to 1.4 in it. The important thing is it's just Mach number 1 that's in there. There's no other Mach number. So everything about the Mach number after the shock depends on the speed and the context of which you were approaching that shock wave or that body in the first place. Density and pressure, they're also in terms of m1 squared. Temperature ratio across a particular standing shock, m1 squared, and basically everything is denoted in that way. Okay. Now, if I asked you to calculate across a shock, how would you do it? Well, this book, they have tables in like this. There are calculators online, and you've got this form of this coming up. Not quite, but almost in this one. This is not a normal shock, this is the bleak one. But you often get graphs as well. And they list all the properties as a function of Mach number. Okay, so we'll get on to the diagrams in a little bit in a minute. So, what have we got here is a summary now. On X is the upstream Mach number, so we're travelling at Mach 1, Mach 2, up to about Mach 10. Here, that's the Mach number in the across the shock. And what is interesting is this red line here. So you see that this is actually, let's see what we got. We should have, sorry, the black line. The black line shows the Mach number after we've gone across this normal shock, this standing shock, one that's vertical in front of us. You notice the numbers, subsonic. So if you design something, a wing or a engine that ends up with a standing shock wave on it or inside it, you've gone from supersonic to subsonic flow. And in doing that, where's our pressure ratio, total pressure ratio, the red one? Oh dear. And you can see the faster you go, the greater the losses. It's not 1 at all. As far as the statics go, static pressure is the green one, and the pressure goes up and up. So the higher the Mach number, the greater the pressure on the other side of the shock. And the blue one is the temperature, maybe not quite so steep, but basically across the shock, the stronger the actual force you're coming, the higher the Mach number, the greater those static values are going to be, and the lower the dynamic values are going to be just after that. Okay. Similar thing here. Mention of this, the reason why we're pulling this one out is to say that this is your total pressure ratio, and it's a reminder here at the bottom. Total pressure is an indicator of how much useful work can be done by flow. So therefore, the loss of total pressure is a measure of efficiency on things like engines. So therefore, we don't like normal shock waves, particularly in engines. We prefer oblique ones if we can get them, because they compress flow, helping with sort of combustion, but they don't lose as much. We've still got more energy that we can use for actual propulsion instead of the heat. Right, does shape make a difference? Very much so. If something's pointed at the nose, then to a certain amount of angle subtended at the nose, you can actually attach your shockwave. If you make it very, very, very big, as you'll see in a minute from that graph that we've got here, depending on the speed you're going, there's a limit to how much you can make this wedge get bigger and bigger. And what happens is, if you make it too wide, so instead of this being about, say, 40 degrees, we make it 60 or whatever, we get this. The shockwave detaches from the body. So very blunt effects, you definitely get a shockwave away from the body. So there are times when we might want something attached and times when we might want it detached. Why might we want a detached shockwave? Go for it. Yeah, to slow something down. Perfect answer. Anything else? Go for it. Someone? Yeah, Stuart? Dissipate heat. Well done. So, if you are an astronaut coming in and you're in a vehicle that's got a sharp nose to it, it better be made of a very, very, very strong substance, because otherwise it's likely to melt. And if it melts, you ain't going to make it. So therefore, that's why a lot of the, certainly when the space race started at the beginning, everything was a very sort of blunt object, because that was the most efficient way to move the heat away and to preserve the life of the people in there. And obviously if you can slow it down, therefore they should reach the Earth at a substantially less speed than go and plough into the ground in a crater. And obviously you're going to have as many parachutes as you can to slow them down. However, in this case, sometimes you do want things attached for the opposite reasons, in a way, because sometimes you don't want the drag, you don't want things slowing down. So if you're doing some sort of military jet or a delta wing effect, a UAV that needs to fly at very high speeds, you just might want to make sure that you can take the temperature at this very either blunt or very, very small rounded tip, just so that you don't have this effect here, which actually ends up with an awful lot of drag, slowing you down. So, depends on what you're actually going to design. Now the thing about the shock waves here is you can see the angle is pretty much, until it gets into the wake, a straight line. So you know what you're going to be calculating soon is what is that angle. If you look here at the right hand picture, you can see that instead of the same angle for the shock, it's changing from basically standing up and then it's going to an oblique shock. So we've got a normal shock here in the red box, and then we've got oblique shocks up here, changes. So therefore, the greatest change in the flow from before to after, if you like, is going to be in this area closest to the nose of the vehicle. And this is the area where the flow is going to go subsonic. When you go across for oblique shocks, you might actually be supersonic, or you could be subsonic. Most of the time it'll be supersonic to supersonic up the top, and supersonic to subsonic near the nose of that vehicle. Okay, so Schlerens. So this looks mostly at the density change. So change the angle of attack, the shock angle changes, fair enough. If you get it too extreme, you might even damage your vehicle and stuff like that. But what's this one on here on the right hand side? It looks like the shock is very, very, very messy. So you can see that up here, there's the shock wave there, and there's the shock wave there, but it looks a bit like it's unravelling. All those lots and lots of waves that have sort of coagulated together in a very small space now look like they're actually undoing. So in fact we've got one branch of the shock there, another one there, another one there, there's a few others. That's called a lambda shock, and the chances are that that's probably a transonic flow. This here is, guess what, our little boundary layer, and that's the cause of what's happening to that poor shock. The shock is unravelling because boundary layers have subsonic parts to them, if not all of the boundary layer. And anything which is subsonic, it's back to the boat, has the ability to move information just if literally backwards. Supersonic, you don't see it coming forwards. And so this shock wave here has actually started, oops, go back, to actually, instead of being a straight line down here, it's actually started to move towards the nose of the vehicle, just due to that boundary layer that's there. So this is a lambda shock, and this will come in a little bit later on the transonic.